The analyst has a tremendous amount of influence over how data is cleaned and what decisions are made about which data points to include and which ones to exclude. And there are a lot of really legitimate reasons for excluding information. And we're going to talk a little bit about what that is and what the choices are that you have to make as an analyst when you get raw data. So raw data is the data that comes to you, whether it's been pulled out of databases or whether people have entered information into a database freshly for your particular study. But most of the time when you get a data set, at first, there are all kinds of issues with it that need to be resolved. We call it data cleaning before you can run analysis. And the main reason for that is we want the analysis to come out consistently. And we want to always know that even though we might be running different models and be using different variables, that we're always talking about the same group of individual observations, that we're not sort of switching around when one observation is included or excluded from different models. So we want to clean the data in a way that we know we can run whatever models we need to on that data set and not be changing it around a lot, so that we're always communicating consistently about the information that we have. So this is a manufactured data set that we have on the board here, and it's intended to represent opinions about satisfaction with schools and teachers. And so there are several variables in here, and it came from a survey of adults, and there are several questions here. So the first one is age. So this is the adult age. This is the person who's actually filling out the survey. The second column is whether or not they have kids. So a 1 is yes, they have children, and a 0 is no, they have no children. The third column is the number of children that they have. The fourth one is their satisfaction with the schools on a 1 to 5 scale. And then the next column is again on a 1 to 5 scale. That's their satisfaction with teachers. And then finally, this attention variable is the amount of attention that these adults perceive their kids having received from the teachers at school. So that's the attention variable. Now, when we look at this data set, you're going to notice a few things right off. For example, you're going to see all these dashes that indicate missing information. That's super common to have missing data in your data set. And that also indicates, in most cases, a data set that's not clean or ready for analysis. So we want to resolve that. We're going to talk about how to handle missingness. And there are different kinds of missingness, and it can mean different things. So we need to be really careful about that. Another thing you may have noticed when I was describing the variables is I said that this satisfaction variable and this satisfaction variable were each on 1 to 5 scales. But you'll notice that there are some 6s here, which suggests to us that there's something going on here that isn't on that 1 to 5 scale. We might want to kind of check out what's going on. That again indicates a data set that's probably not all the way clean. So you want to make sure you always know what the numbers mean in each variable, so that you can watch out for issues like that. Another thing that you might not have noticed is that here in our age category, or maybe you did pick it up, some of you are paying a lot of attention to the items on the screen, but down here we have an observation that seems to be a little bit out of the normal range for age. We have a 311-year-old. So we're going to talk about how to deal with that and how you would look for those things as well. So let's just sort of move left to right through the data set and see what we can observe and how we would handle each of these issues. So the first thing we notice is in this age column, we do have this item down here that's 311, and typically we would call that an outlier. So an outlier can be identified in a few different ways. One of the typical ways is to actually map the data and see if there are any data points that are far outside of the sort of curvature, the normal curvature for that distribution. And sometimes what'll happen is that you have typos that cause outliers that are just wrong, right? So I'm fairly confident that we don't really have a 311-year-old in our data set. So that is likely the result of a typo. When that happens, there are a couple things you can do. The safest thing to do is actually just to delete the entire observation. There's an error in there. We don't know for sure what it is. We're going to clear that out. In some cases, though, especially where you suspect a typographical error, sometimes you can guess at what was intended. And so you can make edits to sort of clean up the data set without losing those observations. You just want to make sure if you do that, that you make a really good record of what you've changed, so that if it turns out you were wrong or you need to run some sensitivity analysis to make sure that you didn't do anything that's messing up all of the conclusions of your data, you want to just know what those changes are that you made. So in this case, I might suspect that whoever was doing the data entry just accidentally hit the 1 twice. 311, as I sort of skim the other ages, it looks like a lot of them are in sort of the 30s range. And so I think it's reasonable in this case, of course I would make a record of this, I think it's reasonable in this case to go ahead and suspect that as a typographical error, and I'm going to correct that down to 31. Now, the other kind of outlier is going to be data that isn't an error. So sometimes you just have really extreme values on something. So maybe we would catch a 99-year-old in our data set, and they may be rare, but that doesn't mean that their data is invalid. But because they're rare, it might change the conclusions that you make and how applicable those conclusions are to the people who are going to be consuming your report. So in those cases, you want to look carefully at your data set, understand where those outliers might be, whether or not you think it's real data. And if it is real data, but it's still outside the normal range, you want to think about whether or not you want to keep it in your data set. And what I usually recommend in those circumstances is that you actually do 2 duplicate data sets, one that includes those outlier values and one that doesn't include the outlier values. And then basically run your entire analysis twice and see if your conclusions change as a result. If they don't change as a result, you can just decide which of those data sets to keep and just explain what you did and maybe identify that there were outliers that you either removed or kept. If it does change the conclusions, that gives you the power then to talk about the differences that including or excluding those outliers causes for your conclusions. And it's something else that you can talk about. You can be fully transparent about that. So rather than having to make a hard decision, you can kind of run it both ways and see if it makes a difference. And if it makes a difference, be really transparent about that. So that's how we might deal with that. So as we sort of move across in this data set, you're going to notice here, once we get into number of kids, we have a bunch of missing data. And when we look at that, we realize that there might be a couple of different things going on here. Missing data isn't the same as 0 all the time. Sometimes, however, it is the same as 0. And we're going to talk about how to do that. But missing isn't the same as 0, in part because 0 is a number and missing isn't a number. So you want to be careful not to put in zeros for missing all of the time, because 0 actually means a number and it is in order with these other numbers and it can throw off the results that you have. Sometimes though, you can look at data and guess at what the correct answer should have been based on prior answers. So here's an example. In this variable, we have whether or not, again, this was a binary variable, whether or not each of these individuals has children. 1 means yes, 0 means no. The next question is, what is the number of children that you have? My guess is, from looking at the way the data is structured, that this set of questions, number of kids, satisfaction with schools, satisfaction with teachers, and the attention that children are getting at school, that those were only asked of people who answered that they had kids. So that's an example of a branching survey where somewhere in the survey there was a question that was asked, and based on the answer to that question, they either saw additional questions or they didn't see those additional questions. So one of the first things you could do with that is say, okay, in this analysis, if these are the variables we're interested in, only people with kids answered these questions, and only people with kids ought to have answered these questions. So we're gonna reduce the amount of information in our data set. We're gonna remove anyone from our data set for this particular analysis that doesn't have kids, because we want to answer some questions about the schools right now, and that's only relevant for this subpopulation. So that's one thing you can do, and that will quickly get rid of these huge blocks of missing data. Another thing you can do, though, is some of those questions, the answer to that first branching question can actually give you the answer to the second question. So for example, number of kids. Well, if somebody indicated that they don't have children, we know that the number of kids they have is actually a number, and that number is 0. So I'm going to enter zeros for those values where they indicated that they didn't have kids. But notice that here we have this 21-year-old who indicates that they do have children, but we don't know how many children they have. We don't want to replace that with a 0 because that is a different kind of missing. This is missing where like we just don't know what the answer is. We don't want to put in a 0 there. We know that's incorrect because of this value, but we don't know how many kids they actually have. So this is legitimately missing data. We're going to leave that for just a second. We'll come back to it. So with satisfaction with schools and teachers and with the attention that kids are getting at school, we can't do this same fancy magic that we did over here with number of kids, because this is just missing data. And in most cases, it's data that we don't actually need, because we're not expecting non-parents to be answering these questions. You will notice, however, that we have this missing observation. We're just going to go ahead and point out that we still have that other one. We have this missing observation as well. So this is someone who has children. In fact, they have 3 children. We don't know how satisfied they are with the schools. We have a sense of how satisfied they are with their teachers, and then we have no information in this attention variable. All the rest of the missing data lines up with folks who don't have kids, but that's still missing and that's still missing. Then when we look at satisfaction with teachers, it looks like the only missing data there is from the branch, so that one's okay. And then we come over to the attention variable, and you'll notice there is a lot of missing information here. So among people who have kids, that one's missing, that one's missing, that one is missing, this one's missing, and this one is missing. My guess with a variable like this is that people just didn't know how to answer it, or they didn't know what the correct answer was. So if the question was something like, how much attention are your kids getting from the teachers at school? They may not know because they weren't there with the teachers at school. So this may have been a flawed question in a way that resulted in a lot of missing data. So we now have a bunch of missing data. I've got little arrows here flagging where that missing data is, and we need to make decisions about what to do about that. So we're going to kind of come down here and look. Here we have this 27-year-old who has 3 children and only answered one of our 3 questions. If we're trying to run models that talk about these 3 variables, that observation is not going to be useful to us. We don't want to guess at what their satisfaction levels were or how much attention the kids were getting. We could really mess up our conclusions if we start making up data for people. So the common practice in this case is actually to delete the entire observation. You just delete them. And what's so sad is sometimes you lose very large amounts of data from your data set because of this missingness. Sometimes you just don't have the data to lose. You have a small data set and you don't want to be deleting observations like that. And in those cases, you can do what's called imputing data. That basically means that you are making a guess, an educated guess, at what that data is, and or that you're filling it in with a value that you think isn't going to mess with your analysis in any negative way. So for example, if we wanted to guess at how many children this 21-year-old has, we could impute a value. One of the things we might do is go find, there aren't other ones in this example here, but you might go and look at other 21-year-olds who have kids in your data set and see how many children on average they tend to have at that age, since you know this person indicated that they have children and they answered these other questions, which gives me confidence that they do actually have children, that's not a typo. And so we need to do something about that data point. Again, totally legitimate to just delete that observation. That's a really common way to handle it. But if we did want to impute that, I might go look at other 21-year-olds in the sample, see how many kids they have on average, and then enter that number here. I might be wrong. And that's a risk that I take. Again, we want to be really transparent about that. So if you're doing this kind of imputation, you would state that in your report so that people know that that's what's going on. Typically that shows up in a data cleaning appendix where you sort of describe this. So in this case, let's imagine that we went and looked at 21-year-olds, and if they had kids, typically they only had 1. So we're going to go ahead and make that guess. Another common thing to do is actually to take the mean or median of the rest of the observations here and plug that value in. I don't super love that approach because I think it's a little bit less thoughtful and a little less systematic, and it can cause problems with your correlations in regression modeling. So I prefer the deletion or the careful consideration and imputing of data if you need to do that. Again, typically with a large data set where taking that much care and attention isn't feasible, you have enough data that deleting the observations is less of a problem. If you have a really small data set, chances are you have less missing data, and so plugging in that one hole or two holes isn't as big of a deal. The other thing you can do, if you have identifiers or if you still have your research key that connects the people's identifying information with your research, you could actually go back, find out who this person is, and talk to them and ask them how many children they have, and just let them know you're just trying to fill in the database from the survey that they took. So that's another approach, is to actually go recover the data. And of course, that would be like top preference, but it's not always feasible. So we've imputed some data. We've talked about some different ways that you could do that. Again, you could use the mean or median of the overall variable. I don't love that approach. You can delete the entire observation. I think that's a more common approach. You can make an educated guess about the value. That's a time-intensive approach. And of course, your most preferred option is to recover the actual data by talking to the person or observing the unit or whatever. Okay, so now what we have is a data set that if we pull out the folks who don't have kids, everything is just kind of clean. The only missing data is these big blocks here, except for in the attention variable. Now, in this case, we have a lot of missing data. And as I talked about before, it's possible and even plausible that the reason there's so much missing data is because it was just a bad question. There's something wrong with the survey, there's something wrong with the question, there's something wrong with our assumptions about what people know or will report on. And so even though we might really have wanted that variable in our model, chances are imputation isn't going to fix this. There's too much missing data for me to be able to make good assumptions about what these values all really should have been. In a case like this, you're going to delete the entire variable. Gone. You're just going to mourn its loss and recognize that it would not have given you good results in the end. We want to keep good, clean data, not junk data. So we would lose that observation. You'll also find as you're doing analysis, if you have really large data sets with lots and lots of variables, sometimes you want to just choose the set of variables that you're planning to do your analysis on and only clean those variables. Totally legitimate to just delete observation or variables that you're not planning to use. And if you change your mind later, you can always rerun your data cleaning code and include those additional variables that you chose to clean out and decided later to keep. So this provides a nice opportunity to just briefly talk about why we love doing our data cleaning in R with scripts rather than doing it manually in Excel, okay, or any other program like that. When you program your data cleaning, you can always start with the same file, your fresh, raw file, and clean it any way that you need to get your end result for analysis. But if you make a mistake, or if you change your mind about how you want to code things, or you want to do some sensitivity analysis and clean it a couple of different ways and run the same code later on slightly different data sets, that is all super easy to do. You just fix the code or change the code, and you can run from that raw data set all the way through, and you'll get your clean data set out again. It's also much more transparent because anyone can look at your code and see what data cleaning choices you made at every given point and how that might have affected the results. So data cleaning with scripts is more flexible. It allows you to more quickly and easily remedy any kinds of problems or changes in decisions that you make about how you want that data cleaned later on. And it's also much more fully transparent when you're sharing that information back out with other people. So we by far prefer that. It doesn't necessarily mean that it's less error prone. You can make mistakes in your data cleaning process in your script, but it's much more transparent because other people can look at and review your code and see if you've made any mistakes. Whereas if you just clean in Excel, all of that stuff is just in your data cleaning notes. Hopefully you keep good ones, And any kind of data recovery or changes in decisions you made mean that you have to then redo all of the manual changes that you made after that. Whereas with script coding, you can just make a change early in the script and you still have a record and functional ability to run all of the changes that you had after that. So we, again, strongly prefer data cleaning using scripts in R.